Hi, this is test prep for test number 9 for EP2P04 in 2018. This test is the one where we add in piezoelectrics and thermal expansion, doing a little bit of multiphysics. So this is test 8 last year in 2017 and 2016. Let's look at the 2017 test 8 to handle this and see how we can work with that framework that we built in general elasticity now that we have other sources of strain. The first question here is, given these different matrices for a material. So we've got a stiffness matrix, we got a piezoelectric coupling D matrix, and we've got a permittivity matrix epsilon T. We are asked to figure out the missing matrices, S, E, and epsilon S. So this is the compliance matrix, the permittivity E matrix, and epsilon S. Okay, so there are equations in the course that in the notes that have gone and directly related all of these things if you need some brushing up on your matrix math. But what I'm going to do for the video is just start with general piezoelectricity and work with these two different equations. So these are the piezoelectric constitutive equations, and let's see. So we've got the first one in the format that gives you stress and charge displacement vector is the stress charge form, and then the second one is a strain charge form, the one that gives you strain and charge displacement vector. So if we copy down the vector form of these, we can grab that one and that one, and we'll be messing around with these. Okay. So the missing matrices, S, E, and epsilon S. First, let's work out how we'd relate these two. So you see that the first, the stress charge form is based on the stiffness matrix, the transpose of this E matrix, the E matrix, and then epsilon S, whereas the other one here is based on the compliance matrix, the D piezoelectric coupling coefficient matrix, and the epsilon T. But even though they're with totally different coefficients here, we can actually relate one to the other by, say, substituting one of the equations into the other one and seeing what we get. So let's just start that off here. So if we take, let's say, just to show you what I mean, we have the stress equation. Then what we can do with this stress equation is substitute in the stiffness matrix. So, or the other equation rather, substitute in for next to the stiffness matrix, the strain, which we know from this equation has to be equal to compliance matrix times the stress plus D transpose E. And now let's see what we got. So the compliance matrix gets multiplied across, and we've got compliance matrix times the stiffness matrix, and then compliance matrix times D transpose E, and compliance matrix and stiffness matrix are inverses of each other. Yeah, so that's still true. You could see that from E equals 0. So maybe we'll say if E is equal to 0, then in order to have left-hand side equals right-hand side, we need CS to be equal to the identity matrix, which means that S is equal to C inverse. So maybe I'll just imply the matrix symbols here. So S is C inverse and vice versa. So that's how we could find the compliance matrix. Now that we know that that's true, the rest of the equation gives us a relationship between the piezoelectric coupling coefficient matrices. So we've got the T's canceling out. So this just says T equals T, so that's gone. And then we can bring one of the E's over to the other side. And if that's going to be true for all E's, then the coefficient matrices in front also have to be true. So because E is a totally free parameter in as far as this equation is concerned, you could apply whatever electric field you like and you still need this stuff to be equal. Then that means we need the left hand side, we need this coefficient matrix to also be the same as this coefficient matrix. So we've got that that's the case. And if you take a transpose of both sides, using the fact that AB transpose is B transpose A transpose, in matrix algebra, you have to reverse the order if you bring the transpose in. Otherwise, the product wouldn't even be defined. So if we don't, if you don't reverse that, then if you don't have square matrices, often it doesn't even work. So we've got E is equal to D times C transpose, but C is symmetric, so that's D times C. So that gives you a relationship for what the E matrix is in terms of the D matrix and the stiffness matrix. So then we'd be able to find that from what we have in the equation here. Yeah, so here's an example of why this was necessary. So D is a 3x6 matrix, and so is E for it to work out in the same kind of a setup here. So you need D to be a 3x6 so that you can multiply it by a 3-dimensional vector and get a 6-dimensional vector, and that's also what E has to do. And sorry, you need D to be a 3x6 so you can multiply D transpose by a 3-dimensional vector and get a 6-dimensional vector, I should say. So D needs to be a 3x6 so that you multiply it by a 6-dimensional vector and get a 3-dimensional vector over here. Same thing for E. So E and D are doing the same kind of dimension mapping in these equations, so you need them to be the same size. They both are 3x6s. So what that means is that this would be a 3x6 times a 6x6, so we're good. If we didn't reverse the order and you just took the transpose of each of these, then we'd have a 6x6 times regular D, which is a 3x6, and that's not defined. With the transpose, it does work. 6x6 times a 6x3, that's all good. Okay, so that's how you figure out the E matrix. Next, we can figure out what epsilon S is by using the other piezoelectric equation here. So this charge displacement matrix one. And we can do the same strategy as we did before, where we just substitute one expression into the other one. So let's start off with this, and we'll substitute in what the strain is. Okay. So D is equal to E times S T plus E D transpose E, big E, electric field, plus, using different notation now, the strain form of the permittivity times the electric field. So that would mean, first of all, what is E times the compliance? Well, if you look back over to this other equation that we had, where E is equal to D times the stiffness, we could work out that by multiplying both sides of this equation by the compliance, E times the compliance equals D times the stiffness times the compliance, but those are inverses, so just the D matrix. Okay, so then what we've got is that's the D matrix times T, and then by factoring out an E, the total coefficient of that is this. But now comparing to the other piezoelectric equation down here, we have D is equal to D times T plus this thing times the electric field. So that part works. We just need this to be epsilon T, and then we're good to go. So therefore, the epsilon T must be equal to this matrix thing that we have. Okay. So there we have it. Okay, now that we have those relationships, we can go and plug these into Maple or whatever computer algebra system you like and work out the expressions for these other coupling coefficients from the ones that we have. Okay, so let's go ahead and do that. So we've got our computer algebra system of choice here. We're going to restart, and we're going to include the matrix package that we're going to use, then we'll say C is equal to a matrix of, now we got to type in the components, 10, 4, 4, 4, 0, 4, 4, 10, 6, negative 4, 0, 0, and 4, 6, 15, 0, 0, negative 4. Now we know that this matrix is symmetric, so that means that this next row here where we have missing elements should be the same as this column of the same number. So fourth row is equal to the fourth column. So the way that I'm going to type this out is actually just by reading the column, kind of looking at that column as I'm typing it, for negative 4, 0, 8, 0, 0. And similarly for the next one, 0, 0, 0, 0, 8, 0, and 4, 0, negative 4, 0, 0, 12. So that, let's just double check that. We can display it so everything seems like it works. Looks like it is indeed symmetric. Seems good. Okay, so because that's in gigapascals, we can multiply the whole thing by 1 E9. And it doesn't display as nicely now, but it did actually input correctly there. Okay, so next matrix that we need is the D matrix. D matrix is matrix 10, 0, negative 10, 0, 0, 0. Now this is just for some material that I made up, so we might have some interesting properties. 0, 0, 0, 0, 0, 0, and 0, 0, 0, 0, 0, 0. Again, this has some interesting units, so that's E minus 12 picovolts per meter. And epsilon T is epsilon naught 8.85 E minus 12 times matrix 600, 0, 0, 5, 0, and 0, 0, 5. That matrix is simple enough that maybe we'll just put it all in one line to save a bit of space. Okay, so there's those matrices. And now that we've got that, we can work out our matrix relations that we've got. So S is equal to matrix inverse of C. We've got D. D we already know, so E is equal to D times C. And we can work out what epsilon T is, or epsilon S. Oh, did we do this backwards? We did, didn't we? Okay, so I just realized that we actually are given epsilon T and we need epsilon S. So if that's supposed to be what epsilon T is, then we can say, therefore, epsilon S is equal to epsilon T minus E D transpose. Okay, so epsilon S would be epsilon T minus E dot transpose of the D matrix. So that one we just called, oh, this isn't going to work because we didn't actually define what D was. Yeah, so E matrix is equal to D matrix times C. I call these matrix because these are sort of strange symbols to have. If you just have something called D, that's often a reserved word. Okay, so there's our epsilon S. We still have positive permittivities. So yeah, everything seems like it's worked out so far. And one way to get this to copy over, if you want to have a neat picture of the matrix and not include so many different significant figures. I find that Maple often, at least in this version, doesn't elegantly copy these matrices over. Like it'll say, oh yeah, in order to get this over, we got to make a bunch of different little pieces of it. So what you can do is just do a screen clip of it, right? So take whatever your favorite screen clipping program is. This is Evernote that I'm using here, but you can use the snipping tool, whatever you're interested in, and then copy that over, and then you've got a nice, more compact picture of the matrix with all the significant figures. All right, the next part says if a cube, 1 meter cube of this, is mechanically free and subjected to a uniform electric field of this, figure out the strains that arise in the material. And now that we have everything in the computer algebra system here, this is pretty simple to do. So we can figure out the strains by using an appropriate piezoelectric equation. So the best one is going to be this first one here. So they tell us mechanically free, that means T is equal to 0. And they tell us that the electric field is this. So let's put that in. So we've got T is equal to vector 0, 0, 0, 0, 0, 0. And E is equal to vector 1, 2, 3. Times 1e6, so meganewtons. And then, using the first equation, S would be equal to little s dot T plus transpose of D matrix dotted with E. And there we go. So we've got a strain that depends on, so a strain in the x direction and in the z direction. And the x direction one is negative what happens in the z direction. So going back up to the coupling coefficient matrix, this matrix only cares about electric fields in x. So you can see after you transpose it a little bit about what's going on there. Let's just do that. So transpose of the D matrix is just this. And then when we multiply this by an electric field, all that's going to matter is the x component. Since the x component is 1,000,000, then that raises the exponent on this by a factor of 1,000,000. So 6 higher is in the exponent. And there we go. So that's the strains. So that's how you would figure it out in Maple. At this point, we can jump over and try to make a formulation for this in FlexPDE. So here's some FlexPDE code that we were dealing with last time. This is this is based on the previous test that we had this year, so one that we were editing in class before. And if we start off with this setup, we can now go and modify it to be the setup that we have in this particular problem. So first we'll get into the mechanical part of the mechanical components of the material before we forget. So we've got 10, 4, 4, and then 4, 0, 4E9, 4, 0, 4, E9, C22, 4E9, 10E9, 6E9, negative 4E9, 0, whoops, made a mistake somewhere. Oh, of course, we don't, we start at 2, 2 when we write these out because we've got the symmetric assertion later. So we're going to start, let's do that again. So 10E9, 6E9, negative 4E9, 0, and 0. C33, 15E9, 0, 0, and then C36 is negative 4E9, 44, 8E9, 450, 460, 55, 8E9, 560, and then 66, 12E9. Okay. All of them are missing, all of them have the exponent afterwards. So that's a common source of error. That looks all right. Then what else do we need? I guess I'll save this as a new file. So you can do that with Control A. Usually that's select all, but that's save as a new file. So maybe we'll call this piezothermal elasticity video. Okay, and next. So that is the new material that we have here, and we've got some boundary conditions on the thing, and we are going to be outputting, looks like some contour plots, and we've got some stress reports. We're not going to need any of that. This conveniently already has a strain reported at the center, so we'll keep that, and we'll get rid of the rest of this. Then, yeah, sure. Maybe actually use some strain at the middle. Just to see how uniform things are. Okay, so interesting strain sort of plots there. We've got some values reported at the end, and that's all we really were interested in this time anyway. Okay, so the material is input and is doing its thing. So next thing we can do is figure out how to add in the piezoelectricity. So this is the definition of the strain itself, and then we need to kind of modify this to see how the stress is going to work differently. So the raw way to enter the piezoelectricity is to go from this equation here. This Hooke's law is kind of like the analog of what's going on in this one. So this is saying the stress is equal to the stiffness matrix times the strain. That's the first part of this. So now there's two different options that we could build in. We could still use this exact equation and then subtract off the components of the E matrix transposed times the electric field. And that would be kind of over on this side. So minus, let's say E11 times big E1. Now notice that, remember that when you're doing this, Flex PDE does not care about cases of letters. So even though we wrote a big E, it treats this the same as a little e, and you have to make sure that you don't have another variable where that's technically called E1. So we have to call the 1,1 component E11 rather than E1. That's a totally different thing to Flex PDE. Then we'd subtract off. Now keep in mind, because you're transposing the E matrix, this gets a little bit weird. We'd subtract off E21, not 1,2, times E2, minus E31 times E3. And then similarly here, E12 times E1 minus E22, E2 minus E32, E3. Yeah, this is one way to do it. So we could go through and edit all of these things in the setup. Another way to do it is to define a different kind of strain. So sort of keep these things up here as like the true strain, and then add down here that there's a part of the strain which is from the piezoelectric effect, and say that that is just this stuff here. So we could say EX piezo is equal to the, and then kind of, you know, go through all of these things, but for piezoelectrics, EX piezo would be the X component of the strain from just piezoelectrics. So that'd be D11 times E1 plus D21 E2 plus D31 E3, etc. for the other ones. And then what we're going to do is we're going to say that EX mechanical plus EX piezo is equal to the total EX. In other words, the mechanical EX is the actual strain minus the piezo strain. And then down here, for all of the stresses, we're going to put those in terms of the piezo strain. So either way, it's totally the same which one you do. I'm going to go with defining different strains just so that we could later, if we wanted to, incorporate some thermal strain a little bit more easily and kind of compartmentalize the different parts of this thinking. So we add an M to the back of all of these to declare that these are the mechanical strains that we're basing it on, which are the strains that are just related to stress. Okay, so first up, nothing should actually change here. EYM is EY minus EYP. EZM is EZ minus EZP. And same thing for the shear. GYZM is GYZ minus GYZP. GXZM is GXZ minus GXZP. And GXYM is GXY minus GXYP. Okay. So we can do the same sort of thing for the rest of the strain components up here in terms of the piezoelectrics. And these again are defining the piezoelectric parts of the strain. So this changes the second subscript and then the third one. Yeah, so D13E1 plus D23E2 plus D33E3 is going to give us the Z component. And then same thing for 4, 5, and the sixth component for XY. Cool. Then all we would need before this will actually run is to define what these D matrix components are. So we should get an error saying that it doesn't know what D11 is when we try to run this. Yeah. So we actually just have to type that in. So looking over at the matrix that we have, D11 is 10, D12 is 0, D13 is negative 10 in the rate units. E minus 12, E minus 12. D14 is 0, D15 is 0, D16 is 0. D21, 0. 25 and 26. And then same thing for the third row. Okay. So now it doesn't know what the electric field is. We can specify that as a boundary condition, maybe at the beginning somewhere, or anywhere. It doesn't really matter where we write it. So let's say E1 is equal to 1E6, E2 is 2E6, and E3 is 3E6. This is for that problem right there where we were defining what the electric field was. So most of the work that we did here was actually in modifying the Hooke's law equation to account for piezoelectricity. And once you've done that once, then you're good to go, actually. This is like the big change to the Flex PDE code for this week to account for that piezoelectricity. And now, with those electric fields, we should be... Ooh, uh-oh. Right, EXP is already a function thing. So how to deal with that? I guess we can't call that EX piezo. Maybe we'll call just that one something slightly different. Ugh. Not really a fan of that. So if you think of a better way to make the variable naming in a way that works, then by all means. Okay. So this probably won't be the same set of strains that we found in Maple just yet, because we haven't set up the boundary conditions just right. So this was supposed to be mechanically free, other than the actually just totally mechanically free, right? We specified no stress, just a strain. Let's see if we can do that. Yeah. Okay. So totally mechanically free, and then we've got our 1e minus 5 and negative 1e minus 5 in the Z, which was the same thing that we figured out in Maple earlier. All right, so far so good. After a lot of setup, we've got our flex PDE agreeing with what we figured out in analytic calculations in Maple. Now we don't get to rest just yet, because the very next part of the question asks us to also include a thermal expansion in this setup, and that means we're going to need to go ahead and modify our piezoelectric equations. So after all of that work, we're going back and analyzing how to change these to account for thermal expansion. So we're not even we don't even get to just substitute in right away. So the first thing to do is to say, all right, well, if we have piezoelectric expansion, then what that does is it modifies the strain. So we're going to say this plus alpha with a little arrow times the change in temperature. So that just directly gives us a different strain, where alpha is a vector made up of the expansion coefficients in all the different directions. So the shear ones are just going to be 0, but then we have these things in those different directions. Okay, so all the strains, so first of all, the strains that would arise from this temperature change alone should just be equal to a delta T multiplied by those strains. So 1 degree, it's gonna, you don't even need Maple to do this. It's just 10 microns per meter, and it's a 1 meter cube, so 10 micron displacement, but 10 e minus 6 in the x and the y for the strains, and 15 e minus 6 in the z is what we get for that. Okay, so that's the overall setup to how we'd modify things differently. Now we have that different strain showing up, and the different stress after we solve for it would be T is equal to the stiffness matrix times S minus D transpose E minus alpha delta T. So you could, if you liked, incorporating things directly into your Hooke's law equation. Let's filter that through C. Yeah, you could figure out what C times alpha is and treat that as a single vector. This one we have another name for. That's our E transpose right there, so that's kind of convenient, but it's sort of the most convenient to work with just this version of the equation and maybe say, okay, that is equal to C times the mechanical stress, and then go ahead and define that the mechanical stress is equal to the actual, or sorry, not stress, the mechanical strain. The mechanical strain is equal to the actual strain minus the piezo strain minus the thermal strain. Okay. Piezo strain, thermal strain. Cool. Yeah, so let's maybe just type down some stuff for visual people. And here's what we got. So this was the piezo strain that we figured out last time. I mean, the stress was 0, so it's just equal to that D matrix times E, although that was the whole thing in the first setup. And now we've got the thermal expansion. Alpha is this stuff. Let's put that down there so we can see it. Alpha is vector of 10, 10, 15, 0, 0, 0 times 1 e minus 6. And then what we're going to do, you can look at that just to double check. Yeah. Now we can say S thermal is equal to alpha times delta T, which is 1 degree. Okay. Now how would we figure that out in flex? How can we account for thermal strain here? Well, similarly from this setup that we did for piezoelectrics, where you have the strain from piezoelectrics written out like that, we can say EXT, EYT, EZT, and then there's no thermal strain in the shear direction, so we just need these three. So ext would be alpha x times delta temp. Careful, delta t is a built-in thing. So delta temp, alpha y times delta temp, and alpha z times delta temp. And now we have new material parameters we need to put in. Alpha x is equal to 10e minus 6. Alpha y is also 10e minus 6. Alpha z is 15e minus 6. And we're going to need to put in the delta temp. Delta temp is 1. Okay, then continuing on from the other expression that we had here, the mechanical strain is now not just S minus the S piezo, but also minus the S thermal. Minus EXT, minus EYT, minus EZT. Okay, so now we're also adding in the thermal strain that we get here. And this would be the sum of the thermal and the mechanical strain. So we've got another 10 microns in the X and Y directions, and 15 microns in the Z, which brings us from the minus 10 microns we had before in Z up to a positive 5, and up to 20 microns in the X. If you want to turn off the electric field parts, you can just set that equal to 0, and then we'll see the thermal effect alone. Maybe it's time to modify the magnification that we've got on this. So we're in the tens of microns. So that means we probably want to magnify by about, let's see, 20,000. It's all linear, so it's hard to tell exactly what's going on. 80,000? Yeah, so you can see some real cube deformation here. Doesn't look much like a cube, or not exactly like a cube anymore. It's all strained out. Okay, so there we go. Next, we're going to figure out the strains that arise from the combined effect of electric field and temperature change. And we actually did this accidentally in the recent part. So the S in Flex PDE, we can add those two strains together. Whoops. In Maple, rather. Maple is case sensitive. So there's the 20 microns, the 10 microns, and the 5 microns. And then back to Flex PDE, we just put both of those strains in at once by adding in that electric field that we got rid of. And there we go, the 20 microns, 10 microns, and 5 microns. We don't have any shear showing up here because the piezoelectric coupling coefficient didn't directly lead to shear stress, didn't lead to shear strain itself. We don't have any boundary conditions on the thing, so there's no chance for the stiffness or compliance matrix to transfer those axial strains into X and Y, into shear stresses or strains, and there's no thermal effect on the shear. So that's why the shear components are staying as 0 in each of these setups. The last part is the trickiest part. This is saying, suppose instead of the applied electric field, the cube is actually electrically isolated so that D is 0 and still is mechanically free. And we have to figure out the total strains that arise from the temperature change now. So we don't have any electric field, we just have a temperature change. We want to figure out the strains that show up. And the way to deal with that is to dive into these second equations. And the question is, which one of these two is going to stay true? So it's actually, as we talked about in class, this first one that still works in this circumstance. So this equation is going to be true. The material moving around is what leads to the electrical effects in the absence of any stress. So this one is true based on the actual true strain that shows up. And if you like, you can substitute in what you have for strain in the event of a temperature change. So if you want to add in the temperature change like we did in the previous setup here to this other form of the equation, then you can figure out kind of a modified stress form of this equation, which is a bit convenient to do if you wanted to kind of analyze analytically how things are working out and get a feel for it. So let's not put too many steps on one line. This thing together is the D matrix, as we saw earlier when we worked out that same thing. And this together with this gives you just the epsilon t. So we're left with a new term that is changing things according to the temperature change. So in this particular case, where we have the D is equal to 0 and the thing being mechanically free so that the stress is equal to 0, we're going to end up with 0 equals that times 0. And the electric field is unknown, but we're going to be able to solve for it from this. So this tells you the electric field is equal to negative the inverse of epsilon t times the E matrix times the alpha vector delta t. And then what we're going to do with that is go and substitute that back in to the stress equation. So we had earlier this total stress setup. And now that we know E, we can substitute that in analytically if you like, and see how things work out. So in this particular case, again, T is equal to 0. Maybe let's show what we're substituting into by leaving that equation alone first, and then we'll put in a 0, and we'll put in this electric field that we got. Okay, so then we end up with a total strain of this, and we can maybe factor out some things that are common to all the different terms. So we're going to be left with an identity matrix minus D transpose epsilon t inverse times E. Kind of interesting. And depending on the material, we may or may not actually end up with a strain based on what this stuff sets up to be. So now that we worked all of that out, we should be able to, in Maple, directly jump right to the end of this particular setup. So this is a new strain that replaces what we had previously. So S is equal to identity matrix 6. Let's just check that that is the right syntax for that. Whoops. Identity matrix. Yeah. So identity matrix 6 minus transpose of D matrix dot matrix inverse of epsilon t dot E matrix. And we're going to have that thing multiplied by alpha and then multiplied by 1. Okay, so we end up with only a small change to the thermal strain that we would have gotten originally. So about 2.3% bigger in X and that much smaller in Z. So that's what we have in this particular case. Let's see how we could work that out in Flex. So to do it in Flex, we're going to go, we need some way to have it figure out what these electric fields are. And that would be the stuff that we haven't incorporated yet, which is this this version of things showing up if D is equal to 0. So we said that the stress is actually is known to be 0 externally to the thing, but we could even build that in internally and say that the electric field is based on the stress potentially, though that might be a problem because it sort of is then kind of coupled in. So basing it on the stress might be an issue, but going back right up to this one and basing the electric field on the strain should work, because the strain is sort of the first set, and then we define the other variables in terms of that. So you can see that the electric field should be equal to the, I guess what's nice about basing it on the stress is that you could solve this out from your D matrix, but we do still need the E matrix there, so that's no good. So let's say that the electric field would be based on the E matrix times the strain, and then multiplied by the inverse of epsilon s. So electric field here, what would that be? We'd have E1 would be equal to, after we multiply by the inverse of epsilon s, it would be negative 1 over ep s 1 times, and then the E matrix times the strain, which would be E11 times EX plus E12 times EY plus E13 times EZ plus E14 times GYZ plus E15 times GXZ plus E16 times GXY. And then similarly for the other components, E2 is 1 over epsilon S22. Because epsilon s is diagonal, the inverse is just 1 over the diagonal components. So that's why we're able to do that so easily. 2, 1, 2, 2, 3, 1, 3, rather, whoops, I'm sort of messing this up. 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6, and then 3, 6, 5, 4, 3, 3, 3, 2, and 3, 1. Okay, so we're going to need to know what epsilon s was. Epsilon S11, was that given in the question? It was not. So we're going to go over to Maple to type these components out. So where's that? Epsilon s is what we worked out right there. And we're also going to need to report what the E matrix components were. Okay, so epsilon S11 is 0.514 E minus 10. Epsilon S22 is 0.4425 E minus 10. And epsilon S33 is 0.4425 E minus 10. Then we're going to need the E matrix components for this formulation to work out. And the E matrix, fortunately, has a bunch of zeros in it. E11 is 0.06, and it's also in units that are near unity. So that's kind of nice. 0.06. E12 is negative 0.02. E13 is negative 0.11. E14 is 0.04. E15 is 0. And E16 is 0.08. The rest of the E components are just 0. So what I'm doing is just reading off the E matrix that we reported in Maple over here and typing those out. We found these earlier from the by manipulating the constitutive equations to figure out the relationships between d, c, and epsilon t. So just again, the E matrix was d times the stiffness matrix. So that's how we figured out the relationships between those. So then, now that we've got all that, we should be able to maybe run it. Nope. We don't have EX. Oh, I put this in the wrong spot. Okay, so we can put this down here. Maybe. Oh, forgot to change this to a 3. Good thing we have those that error handling. And then of course, probably the best error checking we can do is to show that the results that we got here actually agree with what we calculated in Maple earlier. So everything looks good. We ended up with the same result, even though we got it from a very different method. So this one we went and calculated directly what the electric field would be. And in Maple, we went further and sort of substituted that electric field that we would have gotten just from this first equation back into this next part by substituting the strain in, then manipulating forward and coming up with what the total strain should be in terms of a temperature change. So this setup right here, by the way, this I minus this thing, if that times alpha is any different than alpha like it was here, we had a 2% bigger strain in X and about 2% smaller in Z, and that means that the material is actually a very kind of special class of materials called pyroelectric, where you have that a temperature change directly couples over to a strain. So here that's not the case, and as a test you can check that out with quartz and show that it's not the case there either. So that was part E, and that's it. That's the big thing that we want to get across here. So that gets you well on your way to incorporating the piezoelectric and thermal strains into Flex and into Maple, and then working out how these lead to differences in different setups, even in the case of complicated conditions where you don't know the electric field, but instead are just given what the charge displacement vector is. Thanks for watching.